Hello everybody and welcome to my keynote presentation for the euspen Virtual ICE. I want to talk to you today about why we rarely see uncertainty statements on surface, form and texture measurements. Just a little bit of background about who I am. Certainly I've never done a keynote presentation just sitting in my chair in my office at home, so this is a new experience for me. I'm not sure I feel completely comfortable about it. But who am I? So I spent nearly 25 years at the National Physical Laboratory as a principal research scientist, basically working in surface measurement, surface metrology, especially the calibration side of things. In 2015, I took a professorship at University of Nottingham, again working in metrology. Unfortunately, that's not me in the picture there. That's me when I was about 25 or so at MPL. I'm now also the director of transmetrology, which I spun out in 2018 to take the IP from my group out into industry. And slightly more modern picture there. And the final picture shows me just preparing for my latest funding interview in the new world where we don't need to worry about what we've got on down below. And I'm also council member of euspen and on the board of ASPE. So that's enough about me. Let's get on to the actual talk. So being a metrologist, I'm slightly obsessed with definitions and making sure that all my students and people I work with get the definitions correctly. So let's just go through some of these definitions, make sure we're all on the right page. So we're going to define surface topography as everything that's on the surface. So it's all of the spatial frequency features that are present on the surface. Many people call surface texture surface topography, but we're going to talk about everything. So this is the form plus the texture. The surface form is the underlying shape of the part, and often that's determined in terms of a fit to a particular shape. And then the surface texture is basically what's left if we remove the form. So it's the irregularities that are present on the surface, but it does not include the form. So just remember that surface form plus texture equals surface topography. Now we're gonna split this talk into form and texture measurements because they tend to be very, very different fields, but really, we're talking about the same thing. They're all just spatial frequencies. So here's an example. You can see on the left, that's the surface topography. Then there's the surface form in the middle. And then on the right, when we remove that form, what's left is the texture. So second to last definition. So what's calibration? Well, there is a definition in the vocabulary of metrology. I'm not going to read it out there. You can see it's quite a long definition. I'm personally not sure I completely understand it. So here's my definition of calibration. It's a comparison between two measurements, one of which is a reference and the other which is being tested. So calibration is that comparison process, and it's absolutely essential that when we do that calibration process, we have uncertainty in the measurement. And the reason we need uncertainty is because you cannot compare two measurements unless you understand their uncertainty. You just don't know whether those numbers are equivalent or not without a statement of uncertainty. Adjustment, which is often mixed up with calibration, is what we do, how we adjust the instrument to make it comply with a calibration certificate or change the software or something like that. So it's a very different operation to calibration. And then verification is basically us doing some test to make sure it fits to its specification. And it doesn't necessarily involve uncertainty, but often will. And then a CMS, we're going to talk about coordinate measuring systems. So that could be a contact system, or it could be optical systems, X-ray, or whatever. Last definition, I promise, is traceability. Important property, but if not one of the most important properties in metrology, the property of the result of a measurement or the value of a standard whereby it can be related to stated references, usually national standards or international standards, for an unbroken chain of comparisons. And remember, those comparisons are calibrations, all having stated uncertainties, and it's the part in red which is really important. If we don't have uncertainty, we cannot claim that our measurements are traceable. So We're going to talk about surface measurements, and there are modern products these days have very rich surfaces, and you can see some examples here. They tend to have a lot of scale, so you can have textured surfaces on the top of complex freeform surfaces, so you can mix the different scales on the surface. They can have very high slope angles, which, as you'll see a little later, can cause significant problems for optical measurement systems. And they can have a whole range of different types of textures, so from very smooth to very complex textures. And then, of course, along came additive manufacturing and made everything more complex. And this is the key about additive manufacturing. It's not another type of surface, they're just another surface, but the complexity of the surfaces, and certainly the complexity of the shapes you can produce, has now become much more complex. So you can see the example on the left there. You wouldn't typically be able to machine that, but you can easily produce that using additive manufacturing, and it's a highly freeform, very complex shape. So trying to measure that component would be very difficult. And on the right, you can see the texture from an additive component, and you've got all these cavities, thermal cracks, world tracks. There's the world ripples on top of the tracks. So you've got a multi-scale, very complex surface with often re-entrant features, not just high slope, but re-entrant features that make measurement very difficult. So speaking first of form or coordinate metrology, and the most used instrument out in industry at the moment is the contact coordinate measuring machine. And this, of course, benefits because it's been around for a number of decades now. So it has the benefit of a fully developed standards infrastructure for verification, I should say, not for necessarily for calibration, although there are standards available on uncertainty as well, which we'll talk about. It's very simple to model how a mechanical probe contacts the surface. Just model it as a sphere. You might have to consider some contact mechanics, but typically it's much more simple to model than an optical system. There are limitations with the probe, of course, because it's a finite size probe. Then there can be access issues with complex features, and one of the main disadvantages of contact-based systems is that they are or can be very slow. So you have to probe in a pointwise manner. Even if you're scanning, you're still having to take discrete number of points across the surface in a serial fashion. So along came optical measurement techniques over the last few years. Typical examples showing here: photogrammetry, fringe projection, laser triangulation, and these can be much faster than the contact methods. They can give millions of data points as opposed to a carefully chosen few data points. But they suffer from occlusions, shadowing effects of different material textures, and some of the things I'm going to talk about, which make them extremely complex to model. Now you can often make linear assumptions, which make the models easier, but if you're looking at complex surfaces, so you've got very high slope angles, for example, then you're going to have to start modeling using the nonlinear models of the instrument, and it gets very complicated very fast. So how do we calibrate optical coordinate measuring systems? What's the infrastructure that's in place at the moment? Well, if we do a Google search, we won't find anything. We don't have infrastructures or standards in place at the moment for calibration of optical CMS, except in the optics industry. So there has been, for many years or many decades, people have been producing complex optics, and freeform shapes are very popular these days. So there has been a infrastructure put in place for the optics industry, and you will see uncertainty statements in the optics industry. So they tend to have, whilst they may have complex freeform shapes, the level of texture is usually quite predictable. So you don't have a whole range of different types of textures, and typically, not always, but the slope angles are relatively low. So again, you can start using your linear instrument models can be applied. But of course, freeform optics are challenging this exception. There's still many open issues in how we measure and calibrate the instruments that measure freeform surfaces, freeform optics. So the optics industry is slightly ahead. It's one of the exceptions, maybe with the semiconductor industry as well. It's those two are the exceptions where you will see uncertainty budgets. So what is it with the optical systems which causes so much bother? Why are they so difficult to model? It's because if we have the surface texture and the surface texture is captured in the optical field that we get reflected or transmitted through the surface, and we have to extract the data from that field. And that is a complex process. It's there's no other way of putting it, but the optical process of forming an image or extracting the data from the optical field is complex. And if we have multiple scatter, like you can see on the right there, so this is an extreme oversimplification of what's going on, but if you consider the light as just rays that are bouncing off the surface and you have multiple scatter, then that significantly increases the complexity in the models that you use, and I mean significantly. It gets much harder to model, and typically because it becomes a non-linear process due to that multiple scattering, you can't solve the inverse problem simply. So let's just go back to the standards infrastructure that is in place for optical, for at least contact coordinate measurement systems. So the ISO 10360 series, very well known series of standards that covers performance verification of CMS, and there is a part on optical coordinate measurement. Well, there is a part 8 in fact which covers point scanning systems, and then fringe projection and those types of systems, so point cloud type systems, will be covered in part 13, which is under review at the moment. But it's not calibration. It's about performance verification. So it's about giving users the tests they need to say that the instrument is doing what it says in its specifications. 10360 the ISO 15530 does cover uncertainty for contact. It has 3 different methods that are applied. Now we might be able to apply all 3 of these to optical systems. Hasn't been done very much yet. There is some work at least in substitution, but we might be able to apply these, but it's not really been done yet. So if we look at substitution, which is probably one of the easier methods to find uncertainty, and we can apply this with optical systems, and this is where we basically take an object. If we're measuring, for example, the diameter of the sphere here, we put as close as possible to the object we're measuring, we put a length standard with the same or very similar diameter. So we can effectively set the optical system up as a nulling system, or the instrument up, sorry, as a nulling system. And that in that way we knock out a lot of the common systematic errors. The problem is when we're using optical systems, and there's an example in the middle there, and that's an X-ray system on the right, is that we get a very different interaction with the surface due to the complexities we talked about earlier. So that, I put deconvolution in inverted commas there because it's not a linear. Deconvolution is a linear process and it's not a linear process. So extracting the effect of the probe in the case of an optical system is a very difficult thing to do. So it's not clear how we can use and calibrate the substitution method with optical systems. Probably only very simple geometries will apply, and if we've got the complex objects like we showed with the additive surface, then we're going to have problems using this method. The other method which is applied in the contact world is to use a virtual machine. So this is where we have a model of the kinematics of the system, of the CMM, and we then use Monte Carlo methods to propagate the various influence factors through that virtual model to give us an uncertainty statement for a particular object measurement. So let's have a quick Google search to see if we can find if there's any virtual systems for optics out there, and that's what we find. So there are no virtual optical systems. There are developments underway, some of which we'll talk about, but there are no virtual optical CMS. Certainly nothing commercially available at the moment that we can do this with. So we're just going to take a little interlude now and go back to surface texture. So remember, this is we take the surface topography, we remove the form, that gives us surface texture. So it's the fine scale stuff, and typically we have removed the form, so it's the texture that's left on a flat surface, and that makes life a lot easier. So let's talk a little bit about some work that's been done on uncertainty budgets in surface texture. There have been heroic attempts to do this. It's a complex process because of all the filtering that's required and the parameter estimation, etc. But there have been some heroic attempts to do it, at least for stylus instruments with texture parameters. I had a go at this when I was at MPL, and we produced a 56-page document full of equations just for the RQ parameter, for very simple surfaces. And then Han Heigemer has done some work with uncertainty budgets for aerial parameters, which was published in 2015. It's pretty complex stuff. There are some complex equations in there, and it would not be simple for people to apply it in industry. But it's a great attempt, and it was some first groundbreaking work in this area. But there's almost nothing published for optical instruments, and I put published in brackets there. I'm fully aware that some of the optical instrument manufacturers do produce uncertainty budgets for their instruments. I've even seen some, but there's almost nothing published on how to do this. So we decided, and I say we is the ISO committee, so it's some work started by myself and Claudio Zhuszka, who's now at Cranfield University, when we were both at MPL. We decided to have another look at this. Can we make the process a little bit simpler than having to propagate all the equations for all of the different influence factors? So along came this concept of the metrological characteristic, which I'll show you with a picture in a minute. And the traceability is through calibrated material measures. That's the ISO term for calibration standards, usually via primary instruments, which are held at either national labs or accredited labs. So what do we mean by metrological characteristics? And I need to be specific here. We're not talking about the general term metrological characteristics. This is metrological characteristics applied to the surface texture standards. So it has a very specific meaning in that case. So let's discuss what we mean. So in a typical measurement, we have some measurement model, and we have a number of influence factors which affect that measurement model. We propagate those through the model to give us the uncertainty. That's the classic process, the GUM process of uncertainty. The problem is, especially when we've got an optical system measuring the surface, is that we've got very complex influence factors. There's many of them. We may not be able to predict them all because we don't have the models of the system, or we've got non-linear models which we can't solve the inverse problem for. And so this list becomes very long and very complex. So what we decided with the metrological characteristics is that we would try to encapsulate all those influence factors in a small number of metrological characteristics. So these are things that we can determine about the instrument, and also maybe the object we're measuring as well in some cases. I'll talk about that. So we have a number of these things which we can determine with some set artifacts. So we have set procedures which allow every user to find these metrological characteristics for their instrument or object and propagate those through the measurement model. So we still need to have the measurement model, but that doesn't have to include the instrument. It will just be the number crunching part of the measurement model. So these are common to the instruments. So you won't have different metrological characteristics for different instruments. These are defined, and here they are. These are defined for any instrument type, from contact systems to optical systems, and we're even applying them now to X-ray systems for extracting surfaces from X-ray systems. So here they are: the amplification coefficient, the linearity deviation, That with the XY mapping gives you the scales of the instrument, so how it operates in X, Y, Z, and the relationship between those. The flatness deviation, so the reference plane, the measurement noise. Now that's measurement noise, which means it's the noise that you will get when the object is there. It's not the noise of the instrument with no object. So we do have to, that is an object dependent term. Topographic spatial resolution, so that's the resolution of the instrument, and this last one at the end here called topographic fidelity, which is pretty much the things that are left over once we can do these the simple six metrological characteristics above, and then the nasty nonlinear effects, the spikes we see in optical systems, or some of the spikes we see in optical systems, missing points, things like that are then covered by topographic fidelity. Those top 6 are in ISO 25178 part 600, and that defines them, and then part 700 will tell us how to actually determine them using material measures. But topographic fidelity, and in fact topographical spatial resolution, will not be normative in part 700. We still don't have enough information, or we don't have the database there to allow us to work out exactly how to do that and to standardize it. So that was the metrological characteristics framework. That's what we've done for texture, and with that, the instrument users will be able to determine their metrological characteristics and propagate those through their measurement model, and they will be able to come up with uncertainty statements. So can we do this for form measurement? Well, we need to go through the process again. It's not just you can't just take the process we took for texture and take it straight across to form. There are problems with that, which I'll talk about a little bit later. But we need to first of all go through the process of getting all the data and working out what all the various influence factors are for the form measurement systems. That's a complex process, a time-consuming process that we need to go through. Then you need to define what are those metrological characteristics for optical CMS, and define that set of characteristics, and then we can start trying estimate uncertainties and see if it works. And there's pretty much a review stage here where we can say, look, can we use this? Can we use the same sort of framework for metrological characteristics for CMS? I'm not 100% sure about this. I'm betting on it. So I have several students working on this, but whether we can do it or not is still to be determined. So what's issues? So the metrological characteristics, so MCs I call them, so don't get confused with Monte Carlo there. That's MC here is metrological characteristic. So metrological characteristics for texture are object dependent. So, and we spoke about noise being object dependent. Noise is highly dependent on slope angles you have on the surface. It's expected with form, this issue will be even more pronounced. So there's going to be far more issues of object dependency. We just don't have that nice assumption that everything's flat. It's just not the case in the form world. So the fidelity metrological characteristic will be critical in this case because we've got such complex objects. So how do we untangle the random and systematic contribution? So if we typically with a gum type of uncertainty budget, we need to be able to do that, and that's a very difficult thing to do when we've got complex objects. So let's just talk a little bit about noise. So the noise and the random effects, and really you can't really separate the repeatability or the random effects that you're getting in the measurement and the noise. The noise will capture that information, and you cannot really consider it as a random effect at each point. It's more complex than that, and I mean, Hanheimer showed in 2005 that noise actually causes a bias in the measurements. It doesn't just affect in a random sense. It can also cause a bias, certainly for surface measurements. And it's highly correlated, and this is the problem. It's a simple statistic, as a standard deviation at a point, for example, will not capture this correlation of the data. So when we do surface measurements, we're never measuring at a point. there's always some influence factor, there's always filtering going on and things like that. So there's always a kernel which means that the previous measurement is affecting the next measurement point. So we need to understand that correlation as well. So this is why, again, it becomes very complicated. Here's just an example of some work by Professor Christopher Evans in UNCC, here he's measured a surface, and you can see the average height map of a fused silica optic here, and then you look at the standard deviation of the point. So he's done lots of repeat measurements. He then determines the standard deviation at the points, and you'd expect that to either be a flat map, or that it would be somehow correlated with these things on the surface you can see here, but you're not. You're getting this highly systematic effect here, which, you know, in later studies was found to be down to the motion system. But that wouldn't be clear just by taking standard deviation measurements at a point, exactly what's going on and how to model that. So we've been looking at a slightly different approach. It's taking some of the work from Christopher Evans and Heidemer, etc., and taking it maybe one step further, where we're now going to model the surface as a random field, or the measurements as a random field. So if you imagine you've got there you can see at each point in this map we've got some kind of distribution. And of course, remember that it's the correlation between those points which is important, and which we're trying to capture with this. And we can model that. So here we're just randomly sampling and plotting it out again. You can do that at the different scales. Of course, you can do it short range and long range dependencies. So if we just took the standard deviation, then you can see at the top there is the initial probability space that we get just by taking the standard deviation, and that would probably overestimate the noise. So we need to think about those correlations. So we take repeat measurements, and then we effectively run a supervised machine learning process. It's a Gaussian process, but I'm not going to go into the details because we're just publishing this at the moment. And that gives you this updated probability space, which gives us this uncertainty band. So now you can see the topography there, and you get a band of uncertainty, or a confidence in the measurements which you can map. So you're starting to be able to get uncertainty at a point, at least the random effects of uncertainty at a point here. So what can you do with that? Well, you can take repeat measurements. You then need to register those measurements. You can resample from that data using, again, the Gaussian process. Use the machine learning process. We talked about the unsupervised machine learning process to give us that guard band or band of uncertainty around our particular measurement. And that can then be propagated through the particular measurement model to give us an uncertainty statement. Here you can see a couple of examples of, one is measuring the aerial cross section of this particular object, and one is taking some height measurements across the object. And you can see the wobbling around you're seeing there is that random process of resampling the surface and forming a synthetic set of data which allows us to model that uncertainty. But there's still some remaining issues. So we're quite happy now that we are developing, and will publish soon. I can't present the exact details here, unfortunately, because we will be publishing soon, on how to model that systematic effect. So we can work out the random effect on the point cloud. But we still need to find systematic errors. There still will be the systematic effects of the instrument. Now, hopefully, those will be something we can determine, which will give us a function, and we do know how to combine that function with the random processes we've just shown, and that would give us the final uncertainty. So how do we get those systematic effects? Well, some people have been doing this using experimental data with material measures or reference artifacts, and then maybe using methods such as Cridgeon methods to try to extract the systematic map of the measurement uncertainty across the field of view of the optical instrument. Or we can establish virtual optical instruments, so we can have a model of the instrument and find the object-dependent errors in that way. We've been doing that for several instruments. So we just published on photogrammetry, an early model of photogrammetry, which allows us to get the systematic effects. Photogrammetry, whilst being a very simple process, is actually phenomenally difficult to model, as we've been finding. We've been also looking at fringe projection, and there are a couple of groups that are doing this. Also in North Carolina, they've been doing work on fringe projection. And we've been looking at coherent scanning interferometry for a number of years now. We've been working out the theory and models of these instruments. All of them, if you're going to look at very complex surfaces, all of them start to need rigorous modelling, which therefore makes life get much more complicated. But we're doing it. We're establishing these virtual models, which should allow us to build up that systematic map, which can be combined with the wobbly map we get from the type A uncertainties. Okay, coming to a summary. We now have several potential routes. So there's the metrological characteristics route and the wobbly plate or the wobbly cloud and systematic effect combination routes that we can apply. The metrological characteristics approach, we can do that in chunks, as we did with texture. So texture, we still don't know how to do the fidelity, but that doesn't mean we can't put the other metrological characteristics out there, and you can go a long way with those. And these can be fed into industry one at a time, which is what we're doing with texture. The virtual approaches can also come in chunks, so we can solve we can come up with the linear models first, and then come up with the much more complex models later. The statistical geometry, so the wobbly cloud method, as we call it, suffers from computational issues. So it can be very slow and requires a lot of computing resources. That's going to be an issue. We need to work out how to speed that up or to do something simpler. And will people trust a traceability infrastructure with only optical systems? So at the moment, we always go back to check with our contact systems, to calibrate with our contact systems. But perhaps if we've got realistic virtual models, which we've proved out, then we can just use optical-based calibration. And we might be able to do that. So we're getting there, and the tools are almost in place. So let's go back to our initial question. Why do we rarely see uncertainty statements with form and surface texture measurements? And the answer is because it's very, very complex. So the modelling of the optical instruments, the mathematics and physics problems that we need to solve are very complex. Sometimes they're not solved. You can't find them by looking up in the literature necessarily. You've got to get your hands dirty and start actually doing the modelling yourself, and it's complicated. So we typically find that it takes minimum 2 years probably to train up our students to be able to start working with the virtual models, etc. It's a complex process. There's a big learning curve, and then once, of course, we have that framework, we cannot expect our users in industry to start looking at rigorous optics models, etc. We need to start having simpler systems in place for industry to use and push those towards ISO standardization. Okay, just some acknowledgements. I have to acknowledge all my colleagues in ISO Technical Committee 213 Working Group 16, and there's, you can see a bunch of them there. So we've been working very, very hard on the ISO framework, so 25178 part 600, and hopefully towards the end of this year, beginning of next year, part 700 as well. And that doesn't solve all the problems, but it goes a long way to solving many of the problems. So we're very proud of our achievements there. And here's just a few people I should name. Chris Evans, who's been really pushing the work in the optics industry for decades now, and has laid the path for many of us. Claudio Zhushka was my colleague who helped me develop the meteorological characteristics framework when we were both at MPL. He's now at Cranfield University. And Hydramer, of course, who I work very closely with still. He's at Leuven these days. And Peter de Groot there. And Hydramer and Peter Groot, we call ourselves the Three Amigos. So, and we're still working on a review paper at the moment on the meteorological characteristics and trying to solve the fidelity problem. And Nicholas Senin, who's worked with me for many years now, and is the one that's developing the wobbly plates model. Okay, and of course I have to thank my team of researchers. I don't do this work, they do the real work. So thanks to all my researchers, and thanks to you for listening.